Okay, welcome everyone. We're almost there. So some of you asked me about the meaning of 2 square root of d minus 1. So let's talk a little bit about that part. As I mentioned before, you have for the complete graph K4. The exercise for your homework is to show that the cube Q3 is a 2 cover. Okay. Now, obviously, you can think, okay, so where does this go? Like you can have K3, K4, Q3 covers. Is there something that sits above all these covers? And there is something like that. That is an infinite tree. So there is something called the universal cover of a graph. So this is going to be an infinite graph. And in the case of d-regular graph, so my example will be d equals 3. So the universal cover of a finite d-regular graph or finite d-regular graphs is an infinite tree, and you can think of it. I'll draw it this way. And this is an infinite 3 regular tree. And so on. Now, let me show you how this graph covers this graph in the kind of similar manner the way we defined the 2 cover before. Now, 2 there was nothing special about 2. I could have done 3 cover, 4 cover, and so on. Things would have been kind of similar as what happened with 2. Now here, what I want to show you is that from this infinite regular tree, there is a graph homomorphism to this graph, which is finite. So this is, let's say, let me write these vertices as A, B, C, D. Okay. And now here, I will tell you for each of these vertices, I will tell you the image. So I'll define a function from the vertex of this infinite tree to the vertex of K4 that preserves such that it's a graph homomorphism. So X and Y, how do I want to do, yeah. X and Y, an edge here implies X and, f of X, Y. An edge here. Okay. So the way you kind of can define it is you look at this picture and you can say, okay, let's say this is my vertex A, and you look here, what are the neighbors of the vertex A? B, C, D. So I can put here, I can call this B, C, D. So this vertex will be sent to A, this one will be sent to B, C, D. What are the neighbors of B? They will be B, C, D, and that's the meaning they will be sent here, and so on. So this is B, D, and this is B, C. So this continues like this, okay? And now, if you have 2 vertices here which are adjacent, okay, let's pick here C and D, well, that means that these vertices get mapped to C and D here, which is an edge, okay? I could do this, so let me show you how I could do this for something that is not regular. Okay, this can work also for something that is not regular. So let me give you this example. I'll use different numbers here. Let me use 1, 2, 3, 4. Okay, and let me say here I start pick one of these vertices. Let's say 2 has 3 neighbors, and I can label them 1, 3, 4, and then 1 has 4, 3 has 4, and then 2 has 1 and 3. And then you continue like this. And you will get, so this graph, which is finite, will have, this will be universal cover. It's called universal cover. These graphs are called universal covers because if you give me any finite cover of this graph, like if you give me something like Q3, which covers this graph, this cover will also cover it. So universal cover will cover every finite cover of it. Okay, and the same thing here. Okay. Now, for so what happens for you see the picture gets a little bit. You have to adjust your vision here because you're moving from finite graphs to infinite graphs. Infinite graphs, you don't have adjacency matrix, you have adjacency operator. So you're going into like Hilbert spaces and things like that. But you still have something called eigenvalues, and the spectrum of the adjacency operator of this infinite cover is the interval -2 square root of d minus 1 2 square root of d minus 1. And you have something like largest eigenvalue of this cover will be 2 square root of d minus 1, and this largest eigenvalue of this adjacency operator for the infinite graph is defined something like a limit as n goes to infinity of square root of, let's say, order 2n of t to n at u, and this will be the number of closed walks, that start maybe at the root, let's say here at A, and they go for 2n steps and come back. And what is known about this, when you calculate this number of walks, you have to calculate how many ways you can go into this tree and back. And what happens is, because of this graph homomorphism, for in a finite graph, in this finite graph, if you want to count, so this limit will be 2 square root of d minus 1. You can calculate that by doing some combinatorics here. And what will happen is that in a regular graph, if you take the number of closed walks of each vertex, you will get roughly at least 2 square root of d minus 1 to the length of it, something like that. So that's how this number comes in. And then the number of closed walks, you can relate them to the eigenvalues of the graph. Okay. So in the afternoon, I'll give you a different presentation. In the afternoon, I think I'll give you some slides presentation from some talks I've given before, in which I'll give you another explanation of this 2 square root of d minus 1. But for now, I thought I mentioned it that it relates to something about infinite regular trees. Okay, all right. Now, so let me tell you. So we talked about Kirchhoff matrix T theorem, which is kind of meant for pretty much everyone. It's like the first application of eigenvalue methods in combinatorics. It counts something via eigenvalues and so on. Let me give you one of the first application of eigenvalue methods from the previous century, which relates to this notion of Moore graphs. So I don't know if you've seen this, but it gives me an excuse to tell you about strongly regular graphs in a bit more detail. So what is, so Moore graphs, this problem was studied by Moore in 1950s, and what was the problem? So you are given two numbers, the degree, greater or equal to 2, and capital D, which is a diameter. Find, connected D-regular graph of diameter D with maximum number of vertices. So let's call this maximum number of vertices n of dd. I'm sorry, okay. So I give you a degree. So, and we want to find in a diameter d, find the maximum number of vertices in such a connected graph. Okay. Okay, easy stuff. d equals 1, there's only one graph. What graph do you know with diameter 1? Complete graph, and d regular, so and d1 is d plus 1. Because there's only one graph, complete graph k, d plus 1. Okay? So, another easy case, d equals 2. Cycle. So which cycle? If I give you the diameter d, okay, so he says cycle twice d. Can you do better than that? Cycle with 2d is 2 regular, has diameter d. Can we make a bigger graph? Cycle with 2d plus 1. Okay? Okay, easy. All right, so from now on, let's look at degree at least 3, d greater or equal to 2. Give me your favorite d greater or equal to 3. 3, very good choice. Give me your favorite capital D greater or equal to 2. 2, very good choice. Oh, everybody's tired, they don't want to work. Okay, so how big can you make the graph? Peterson graph. Oof. Okay, so NDD, because of this construction, is greater or equal to 10, because this graph has 3 regular diameter 2, and 3, 2, is it actually 10? Can you make anything bigger? Well, I have a vertex. What's the biggest I can do? I can take a vertex, I have 3 neighbors. Each of these, because it's 3 regular, each of them could have 2 more vertices here. I cannot go further down because the diameter is 2. So the largest number of vertices I can do is 1 plus 3 plus this, so n3, 2 is at most 10. So in general, so this is, let me tell you first, this is called Moore bound. And Moore bound says that n of dd is less than or equal than 1 plus d times d minus 1 plus d times d minus 1 to the power d minus 1. And why is that? Because this bound comes, you take a vertex, you have d neighbors here. So this is the biggest number of vertices that you could have. When you stretch, the graph is as stretched as possible. So here you will have d times d minus 1 to d minus 1, because you keep going like this, okay? And because the graph has diameter d, you cannot have more than that, okay? So this is called Moore bound, and it gives you some bound. Now let's do something easy. Okay, so we did d equals 3. D equals 3, capital of D equals 4. 4. We'll do this. 4. We'll do this. So this picture tells me that n42 will be less than or equal than 1 plus 4 plus 12, which is 17. So this is an upper bound. Just because I have this picture doesn't mean there is a graph with diameter 2, which is 4 regular with that many vertices, because this is the most that the graph can have. Okay? So the N42. Aye? Complete bipartite K44. Okay, that will give you N42 greater or equal to 8. Okay, so the problem becomes interesting very quickly, interesting and difficult. Let's see what this Moore bound gives you for let me write it here, for diameter 2 in general. So for diameter 2, if you do this picture, you will have just as before. You have one vertex here, you have d vertices here, and you have d times d minus 1 vertices here. Okay? So the number of vertices in your graph ND2 is less than or equal 1 plus d times d minus 1. And when you do the calculation, this becomes d squared plus 1. Okay? So here's the result. So this is a theorem due to Hoffman and Singleton from 1960. And he says that if ND2 equals d squared plus 1, then d has to be 2, 3, 7, or 57. So the only time when you can attain equality here in this inequality will be if d equals 2, or if d equals 3, or d equals 7, or if d equals 57. So by this theorem, here we know for sure N42 is not going to be 17 because d is not on that list. Okay. So let me give you a proof, because these numbers look like, okay, a bit strange. Is, you know, you can try to think, oh, primes, but obviously 57 is not a prime, and so on. And so let me give you a quick idea about how this let's see how quick that is. I'll give you an idea about how this is proved, because this is done with using eigenvalues. Okay, so I'm going to leave this problem here, kind of like, okay, and I will go back now to strongly regular graphs, because we will need the machinery from strongly regular graphs to solve this problem. So as before, I'll go back and we have this notion of V, K, lambda, mu, strongly regular graphs. And we did this thing a few days ago, and we proved that, let's say this is connected, and we have eigenvalues k, eigenvalue r, and eigenvalue s. Does anybody remember how we can find them quickly? R plus s is lambda minus mu, and r times s is mu minus k. Okay? And then for this problem, you will also have R and S will have multiplicities, F and G. And these multiplicities, you can get them by saying that F plus G equals V minus 1. And from the trace, you will get that F R plus GS equals minus K. Because that's the trace. If you put K over there, you get the trace. And okay, so these are the eigenvalues. Now, from here, again, you can get explicit formulas for R and S. You can get explicit formulas for F and G. When you give me, so I'll tell you, not a big secret, but when you give me a family of like you give me the parameters, this is what I'll use. you take lambda mu, you have R plus S RNS. And I'll show you in a second that in most of the cases, RNS will be integers, so you can get them right away. And then, once you get RNS, you can find F and G by solving this linear system with RNS, okay? So, you can also, from these things, you can get closed formula for RNS, which I will write, but if you want to remember them, do them, but these are the easiest thing to remember for strongly regular graphs, these formulas, okay? So from here, like I said, you can get R to be lambda minus mu plus square root of the delta, which will be lambda minus mu squared plus 4 times k minus mu over 2. And you can get S to be lambda minus mu minus square root of lambda minus mu squared plus 4 times k minus mu over 2. Okay? And for F and G, let me see if I have them written down. I don't think I have them. 1 second. You can find this in the Brouwer and Hammer's book, which is available on the internet. You can find it for free, and you can. I mean, we can deduce them, but I'm not going to do that in the last lecture today. So I'll just give you the formula, and then in the afternoon, if you're interested, we can calculate them. So F will be 1/2 of V minus 1 minus. Here there will be a fraction R minus S at the denominator, R plus S V minus 1 plus 2k. So that's the F and that's the G, 1/2. Okay. Now, so this is the gist of what happens for strongly regular graphs for eigenvalues and multiplicities. You'll have 3 distinct eigenvalues, and those are the multiplicities. Let me erase here. So from there, you can get the following. So if you have one of these parameters, v, k, lambda, mu, you will have 2 possibilities. You will have a possibility that R and S are integers. And like I said, in this case, you can calculate the eigenvalues easily with that formula and the multiplicities. And otherwise, if R and S are not integers, in this case, the parameters v, k, lambda, mu, you can prove that you know exactly how they look like. And the parameters will look like something like this: 4t plus 1, 2t, t minus 1, t. Strongly regular graph. And these are what are called conference graphs. Okay. So it's not too hard. Maybe we'll go over it in the afternoon. But again, for strongly regular graphs, you see like this R and S. As you look at it, they're conjugates of a quadratic, but it can happen for them to be integers. So if they're integers, you're happy. If they're not integers, you're also happy because you know how the parameters will look like. It will depend just on one variable. And 4t plus 1, 2t, t minus 1t. Paley graphs, for example, are example of such graphs, but they could be others. Okay. All right. Now, if we come back to this problem, so let me kind of draw parallel with what happens here. I claim that, so assume that gamma is a connected graph, connected deregular graph, with diameter 2 and d squared plus 1 vertices. Okay? So this graph, in some sense, is kind of the most stretched. It's the largest graph that you can make with diameter 2 and d regular, okay? So you have, again, so here you have one vertex, here you have d, and here you will always have d times d minus 1. Now, in order to say something about this graph, you have to analyze its structure a little bit. And first I will say the following. I will have claim 1. Gamma contains no triangles. Okay, what's the idea? Why does it contain? So let me move it here so that we can do the proof easier. So this triangle is not containing gamma. Well, let's see what happened if you had a triangle. So by contradiction, if gamma has a triangle, let's call it x, y, z, then here's a picture. We look from the perspective of x. X will have d neighbors, but y and z are adjacent to each other. Okay, so compare it with this this picture that I showed before. You want to have d here, you want to have 1, and you want to have d times d minus 1 here. That's your graph. Here you will have 1, that's okay. Here you will have also d, because these are all the neighbors. Now, this vertex y, how many vertices is it gonna send down? D minus 2, because it loses this edge here. So this one sends d minus 2, this one sends d minus 2, and the remaining ones, each of them may send d minus 1, okay? But here, what you will get less than or equal. For these two vertices, you have d minus 2, plus for the remaining vertices d minus 2, you can have d minus 1. You know, because here they could send the most d minus. But you will never, this thing, it will be strictly less than d times d minus 1. Okay. I mean, in order for this to work, everybody would have to send d minus 1 down. But these ones are not sending, so that's another way of saying, okay? So that's the first claim. Claim 2, gamma contains no C4s. So no cycles of length 4. And the proof will be similar to this one. Yes? So which one am I looking? Where am I looking? Here?
Not in third level.
Yeah. Yeah, but you can always look at it, you move it here. So what I'm saying is, this graph, it has to be the most stretched. So for this graph that is the most stretched graph, the one with d squared plus 1 vertices, you cannot have a triangle anywhere. Because if you have a triangle, you look at from the perspective of a vertex in the triangle, you have a vertex here, you have d neighbors here, but here you cannot get that many vertices as you want. You will have fewer, because you lose an edge here. So this one it's not d minus 1. And the same argument will apply now. We'll do the same argument to show that it contains no C4. So let me erase here. So claim 2, So by the same by contradiction, assume that, let's say call this A, B, C, D belongs in gamma. Let's assume that you have a C4 that is in gamma. You start at the vertex A, you have here B and C. Here, again, in total you will have D vertices. Now when you look down, B and C, they have a neighbor here, D. And they may have something here, they may have something here. But together, they, oh, not D, I used the A, B, C, F. This is F. Okay, so these vertices here, they send, each of them sends at most D minus 1. But B and C together, they have a common neighbor here. So in here, they send at most 2D minus 3. Because each of them sends D minus 1, but they will overlap in one position. So whereas here, if I had any two vertices, they have to be disjoint, and they would send, like if you look at this would be 2D minus 2. So because of this, because they overlap here, the number of vertices here is also going to be strictly less. So in total, the number of vertices here will be strictly less than D squared plus 1. And that's again a contradiction. So therefore, your graph doesn't have to have any C4s. Okay? So you have no no triangles, no C4s. So from these two claims, so from claim 1 plus claim 2, I get that gamma is actually a strongly regular graph with the following parameters. D squared plus 1 vertices, D regular. Because it has no triangle, lambda has to be 0. And I'll show you in a second that the mu has to be 1. Okay? So remember, this is a number of vertices, which we know. D is a valency, which we know. Now, 0 comes because no triangles. Okay, so the graph will be, so here you don't have any triangles as we that's claim 1. Gamma, this is vertex X, gamma 1 of X. And now gamma 2 of X claims that if you give me any vertex here, let's say Z and X have exactly one common neighbor. Now, the graph gamma has diameter 2. So gamma has diameter 2. So because gamma has diameter 2, it means that Z and X, when they're not adjacent, they have to have at least one common neighbor. Okay, so that implies if I look at the neighborhood of X intersect with the neighborhood of Z, this has to be greater or equal to 1. But if it is 2, what is this graph? A C4. So by claim 2, you get that gamma 1 intersect of X intersect gamma 1 of Z is exactly 1. And that's okay? So from these combinatorial constraints, this graph is the most stretched graphs. You get immediately that this graph is a strongly regular graph. And then you put it now through the machinery, we'll put it now through the machinery of strongly regular graphs. Okay? So, any questions so far? It's okay? All right. Okay, so let me erase here. So now you have this graph with, which is strongly regular graph, and now we have two possibilities. So this graph will have eigenvalues we'll have eigenvalues D's role of K now, R and S, multiplicity 1, multiplicity F, multiplicity G. And now we have two possibilities. Either R and S are integers or R and S are not integers. Let's deal with this one first because this one is the easiest one. If R and S are not integers, from what I told you earlier, what it implies is that these parameters d squared plus 1, d, 0, 1, they have to equal, they have to look like something like 4t plus 1, 2t, t minus 1, and t. Okay? So that means from when you identify this, that t has to equal, t minus 1 is 0, t is 1, so t is 1. And so 4t plus 1 is 5, so that implies that d equals 2, so that implies that d squared plus 1 is 5, so you have 5, 2, 0, 1. Do you know of a graph that is 5 regular, that is 2 regular, on 5 vertices, no triangles, and C5. So that forces you to be C5, and this is how you get D equals 2. Okay? Now we will go to the other part, and we'll try to figure out what happens. So let me erase here. Now, what else do we know about RNS? So RNS are integers. Where can we find them on the blackboard on the left? Question? Yeah. Yeah. So you see them here. Like you have R plus S is this, R times S is this, and what you get is that R plus S equals how much? Minus 1, very good. So you can say S is minus R minus 1. And then R times S equals 1 minus D. So we can rephrase this as D equals 1 minus RS. And we can get D as D is 1 minus R, and S is minus R minus 1. And this will be R squared plus R plus 1. Okay. So if this happens, this is what the degree should be. This is what the smallest eigenvalue should be. But now we have to have some courage, and we have to go into here. Now, before I go into here, which, don't be scared, F, what kind of number should F be? Integer. So because it's an integer, this number should be an integer here. So because F and G are multiplicities, they're integers, so from over there, from that part, I should have that R minus S divides R plus S V minus 1 plus 2K. Okay. R minus S. S is minus R minus 1. So that's going to be 2R plus 1. R plus S, we already did it. So it's minus V plus 1 plus 2K. Okay. Now you can imagine V is a larger one, so we will rewrite it in the following way. Let me erase it here. Two R plus 1 divides V minus 2K minus 1. Now, I have the not k. The k for me is vk lambda, so that's going to be d. Now we have the d here. D, I just calculated d is r squared plus r plus 1. And now the v, what is v? Is d squared plus 1. And yeah, I know you want to do this on a Friday afternoon. It's this thing plus 1. Okay, I'll just leave it like this. Okay, so now you will get 2r plus 1 divides this r squared plus r plus 1 over 2 minus 2 r squared plus r plus 1 minus 1. Here I had minus v plus 1 plus 2d, so I change the sign, so it's v minus 2d.
No, this is fine. E is r square plus r plus 1 also plus 1 is there.
Yeah. Oh, okay. Plus 1 here. Plus 1. Okay. Thank you. Thank you. Okay. So, where are we with exercises? 33. So, you should be happy because the exercise is, so this is 33 or 34?
I think this 33.
33? Okay. Exercise 33. Calculate that. That's easy. Part A. Calculate this. Okay, easy. You can give it to, okay, yeah.
This is 34.
34. Oh, yeah. Okay. But the second part is prove that if 2r plus 1 divides this quantity that you just calculate, then r has to belong to 3, 7, or 57. No. R, this r is no. That's the d. Let me see what r is. R will be 1, 2. You can kind of pick it up from here. D will be 3, 7, 57. So r will be 1, r will be 2, and r will be 7. Okay, so this will be a divisibility. So this is just you have to do, so over here you will get something like r to the 4th something. And now, just to kind of save you the trouble, if you do divisibility of, this will have integer coefficients, you divide by 2r plus 1, you will get in trouble, you get some fractions. So instead of doing that, this will be equivalent to 2r plus 1 divides 16 times this polynomial, r4th, and so on. Because 16 and an odd number are co-prime. And then if you do it with 16 times r over 4, when you do the divisibility, the quotient and the remainder will have integer coefficients, and it will be integer, so you will know what divisibility happens there. And so if r equals 1, 2, and 7, d equals r squared plus r plus 1, and then d will equal 3, 7, and 57. So this result, what is at the base of this result? At the base of this result is that the multiplicity of an eigenvalue has to be an integer. That's all. Okay. And so you should also be aware that this result is an implication. So if this happens, d equals 3, 2, 3, 7, or 57. The converse, it's a different story. So this is the first part. The second part is for d equals 2, you're going to have C5. So that's the only graph you can. For d equals 3, if you look at it a little bit, even from there, you will have something like a strongly regular graph with parameters 10, 3, 0, 1, strongly regular graph, and this will gonna be the same thing as Peterson graph. So that's the only graph. So you should, it's a good exercise to prove that this is the only graph that has those parameters. When d equals 7, in this paper, Hoffman and Singleton, HS, they constructed such a graph. And they didn't call it this is a graph that is called now Hoffman-Singleton graph. They didn't call it that, they called the graph G. Now it's called, you know, Hoffman-Singleton graph. And now this is 5701. So this is a 57 regular graph on 50 vertices. There are various descriptions of it. If you go into the book by Brouwer and Hammers, they give a description that is from pentagons. They show you how to build this graph from 10 cycles C5, 5 of them drawn as you draw normally, and 5 of them drawn in a complementary form. And they tell you how to wire them together. And now for d equals 57, this is not known. So nobody knows if this graph would have 3,250 vertices, 57 regular, 0, 1. And nobody knows if this graph exists or not. I tell this story many times. I know people, so experts in this area, who believe that this graph exists, but just we are not smart enough to, you know, who can argue that, you know, okay, we haven't found the graph. So that's one argument, that, okay, this person is an optimist, believes the graph exists, it's just we haven't found it. And I know people who believe that this graph doesn't exist. And I'm more on this side of the negative, that it doesn't exist. And the argument is that for this, for the Peterson, for this Hoffman-Singleton, and for the cycle C5, all these graphs are very symmetric. These graphs are very nice, they're very beautiful. And I know we haven't talked about it either, but what it means is that their symmetry groups, these automorphism groups, their automorphism groups are very large. So for the cycle C5, the automorphism group, you can do all the rotations, you can do all the reflections, so you have order 10. For Peterson graph, the symmetric group on 5 elements, like I show you how Peterson graph is the Kneser graph K and 2, so the vertices are 2 subsets of a set with 5 elements. You can permute those 5 elements any way you want, you'll get Peterson graph. So the automorphism group of Peterson graph has cardinality 125, 5 factorial large. I don't remember off the top of my head the size of the automorphism group here, but it's also very large. So this graph is also very symmetric. Now for this graph, even though we don't know if it exists or not, people have been able to prove that if the graph exists, the automorphism group here should have order at most 300 or 200. Now this is a graph on 3,250 vertices. Peterson graph by itself has 125 automorphism. So this graph, if it exists, is not going to be as pretty as the other one. So for me, it's kind of, yeah, I'm on the side of that it shouldn't exist, but nobody knows. If you look on arXiv, if you check arXiv in combinatorics, every so often there will be some paper saying that this graph, claiming that to prove that this graph doesn't exist. And then later on will be another paper saying that, okay, the first paper was wrong. So if you look, for example, if you go on Andres Brouwer webpage, you will find there recently, like as of this year or last year, a paper in which he goes through all these papers that claim to prove that this graph doesn't exist, and he shows the mistake in every one of them. So I think he got tired of it, so he wrote one paper too. So this is still it's not, we don't know. Okay. Now there's more to it. So let me I'll erase here on the right. So there's more to it. So this is for diameter 2, okay? And you can do it, like I said, we can do it here. It's a little bit fast, but we could do this by, you know, with our bare hands in a few hours and prove this result. There's something that happens for larger diameter. So if degree is greater or equal to 3, and the diameter is greater or equal to 3, then there are no connected D regular graphs of diameter D attaining equality in the Moore bound. So this was a result that was proved independently by Damerel and independently by Banai and Ito in 1970s. So Damerel, I think, it was from England, and Banai and Ito Damerel is from England, and Banai and Ito are from Japan. And so what this says is that if you take larger diameter, and you're saying, okay, you know, you calculate the Moore bound that I said, 1 plus D times D minus 1 and so on. You will never be able to find a D regular graph of diameter capital D that attains equality here. So you see, I gave you here D greater or equal to 2. For D equals 2, you'll always find an odd cycle, the odd cycle. So that works, C 2D plus 1. But for D greater or equal to 3, it doesn't work. And these proofs, these are more involved, and they use the idea of something called distance regular graphs. And it's kind of, in some sense, similar to here. You look inside, if you prove by contradiction, you assume such a graph exists, and then this graph is something called distance regular graph, which is just a generalization of a strongly regular graph for larger diameters. I'll tell you in a second what exactly it is. And then the work there is a little bit more involved to get a contradiction, okay? So this is done in the 70s. Now, if you're interested in this type of problems, there is a survey. If you go on electronic journal of combinatorics, there is a survey about these parameters and the delta. So, you know, pick your favorite numbers, you look there. You know, people have done a lot of work. So this is upper bound, you cannot attain it. So you can take 1 from the upper bound or something, and now that's your new upper bound. But then, you know, people are trying to calculate this for various values, and there is a survey. So you can find there, you know, you get a prize to find if you tell me what N42 is, because we drew the N42, and because of Hoffman-Singleton, it cannot be 17, so this is going to be less than 16. But what is the exact value? What is the largest 4 regular graph you can construct with diameter 2? Okay, what do I get? We give them one of those, the donuts. What is,
One extra.
One extra. You get 1 extra. You get 1 extra if you figure. But this is interesting because you'll get an idea about the tool. So if you want to find upper bounds for this value, and you need to get some proof, and most of the proofs are going to be algebraic. If you want lower bounds, you want to have constructions, construct graphs that have many vertices with these properties. So, you know, people are trying to go from both ends at it. Okay. All right. Okay, so again, I know it's Friday afternoon, you're tired, and the last thing you want to do is get another topic on your, landing on you right now, but I'm sorry, we'll do a little bit of this, but it will be just some light stuff. So I'll tell you what the distance regular graph is, some examples, and then we'll finish up. Okay, I have. There will be pictures. Okay. So. So what is a distance regular graph? So it's a extension of a strongly regular graph for larger diameters. So we have let d be greater or equal to 2. A graph gamma is called distance regular. Distance regular of, let's say, of diameter d. If there are some numbers, and now don't be scared, okay? If there are some numbers b0, b1, bd minus 1, so you have d numbers, okay? And then you have other numbers c1, c2, cd, also d numbers. Natural numbers, such that, so I'll draw the picture here. I will take a vertex x, here I have the neighbors of x, here I'll have the second neighbors of x, here I'll have the vertices at distance I minus 1 of x, here the ones at distance I, here's the distance I plus 1 of x, and here at the end maybe gamma d of x, the last one, okay? So the property of distance regular graph is, informally, is the following. You pick a vertex, kind of like we did for strongly regular graphs, and you kind of hang the graph from that vertex. I mean, in my case, the hanging is kind of to the right, but think about this, look at it this way, okay? So you have the vertex x, you will have, in the second layer, you have neighborhood of vertex x, here vertices at distance 2, and so on. What will happen is that this partition, for any vertex x, this partition will be equitable, and with the same quotient matrix all the time, for every vertex. Now, what that means in terms of graph theoretic terms, it means that for any I from 0, 1 to d, for any vertices xy in V with the distance between xy equals I. So for me, I have x here, and I will have a y here. So x, this gamma I of x, so for me, gamma I of x contains all the vertices z such that the distance from x to z is I. It's the i's distance neighborhood, okay? So what happens is for any xy distance I, when I look here, this vertex has neighbors, okay? This vertex will have neighbors. The neighbors of y, where can they live? They can live further away from x, they can live closer to x, they can live in the same place as y. Well, what happens is the number of vertices that live here will always be this number bi. So the b's are going to be the numbers that go forward, okay? So for any x and y with the distance between x and y equals I, the cardinality of, so gamma 1 of y, which is a neighborhood of y, intersect with gamma I plus 1 of x equals bi, okay? The number of neighbors of y that live closer, this will be ci, and obviously you can ask, okay, what about the neighbors? I'll tell you about those in a second. The number of neighbors of y that live in the same place as y. Okay? But you see the b's, that we list the b's first. The b's are the numbers that move you forward, okay? So if I was here in the first, if I equals 1, then if I look here, this is B1. And if I was here in gamma 2 of x and I look back, what is this? C2. Very good. If I am here and I look back, this will be C1, and we can tell that C1 is 1 because you go back, you'll be 1. Also, we can tell one more thing. What is B0? If I take B0, I take y equals 0 here for any x and y that are a distant 0, means they are the same. The number of the neighbors going forward is always going to be B0. So what does it mean about the graph? The graph will be regular of valency B0. So B0 will denote it by K, and this will be the valency of gamma. So from the definition you get forced that the graph has to be regular of valency B0, and people call denote B0 by K. So now if we come back to this y, Bi going forward, Ci going back, how many here? The rest. K minus that. This is usually called AI because if people are lazy to write more about it, you know, you have Bi, Ci, and you know, but you know that this AI here, it will be K minus Bi minus Ci. Okay, so now let's draw some pictures. Let's see. Let's start with something small. Okay, let's see, what picture do I have here? Okay, let's start with the Q3. So the way I drew the cube for us, it was like this kind of three-dimensional picture, but now I will draw the cube this way. So you can think about the cube of vertex. It has 3 neighbors, and then here what you see is essentially you see a C6 in between these parts, and then you go back to the end. This is the cube. It's drawn in a different way. And now from this picture, so these numbers, you put them into you can write these numbers like this way: B0, B1, BD minus 1, C1, C2, CD. This is called the intersection array. Of gamma. And also, because we don't want to draw this picture all the time like this, you draw this picture in what is called a distance diagram as follows. So for a general graph, you put here the blob, which represents the vertex here. How many vertices do we have here? We have 1. And then here, you put a blob that represents the vertices here. How many vertices do we have here? K. And then you put a blob here, let's say this is K2. You go and you go all the way to KD. And then what you want to do is you want to keep track of how many, what happens in between these blobs and what happens inside the blobs. So from this vertex, how many edges go in here? All of them, K, so you write the K here. From this blob, each vertex, how many edges sends back? Exactly 1. From this blob, how many edges does each vertex send forward? It's not K, it's... No. Forward. It will be this B1. And so here, inside the vertex, you will be A1 regular, inside this blob. And then you do the same thing. Here you will have C2, B2 forward, A2. Here you will have CD going back, AD going back. Let's see it for this graph. So for the cube, so the distance diagram for the cube, you have one vertex here, you have 3 going forward. Here you will have 3, you have 1 going back. Inside here, no edges, so when there's no edges, you can put just the dash like that. Going forward, you have 2, here you have 3. From 3 going back, 2. Over here, dash, going here is 1, 1, and 3. Okay? So the whole, you know, a picture is 1,000 words, maybe not 1,000, but a few, you know. This is the picture for the cube. This is a distance diagram for the cube. For example, let's do the one for Peterson graph. Because Peterson graph is also a distance regular graph, but of diameter 2. I have a vertex, 1. How many neighbors? 3. 3 going forward, 1 going back, no triangles, so there's nothing here. How many do we have in the last blob? Because it's diameter through. 6. 3, you have 2 going forward, 1 going back, and we talk like in this here you have cycle C6, so you have 2 here. Okay? So that's kind of how you can represent these graphs very very easily.
Determined is this.
Huh?
Is the distance regular graph determined by this distance diagram?
Not necessarily. There are some. So there are some graphs. You know, Peterson graph is and so on. But in general, you don't know. It's actually because it's also the same question for strongly regular graphs. Just because a strongly regular graph, you have some parameters, it doesn't mean that you know, you'll have the, no. So let me give you an example. So for example, let me do one more example here of a strongly regular graph. We did this graph in class before. So this one was 9, 4, 1, 2. Strongly regular graph. But if you want to do the distance diagram, you have a 1 and you have a 4 because it's a 4 here, okay? So you have a 4, you have a 1 back. Then you look what is inside this 4 in the neighborhood. What's the valency? The valency is this 1. And that kind of tells you what you have to go forward because you have a 1, you have a 1, and the graph is 4 regular. So what's going to be here? It's going to be 2. Now, here, this is your graph. You have 9 vertices. So you have 1, 4, 4. This here is the parameter that tells you how much you go back. It's going to be 2. And then you have a 2 here. So this is the vertex, let's say X. This would correspond to here. The neighborhood of it is this one here. And that corresponds to here. And you see what's left is the cycle C4, and that corresponds to this block. Okay? Now, I can do this picture for any 3 by 3, it doesn't matter. I can do 4 by 4, I can do 5 by 5. They're all going to be strongly regular. So here's the one that is, so 4 by 4. So each row is a click, K4, each column is a click. You know, K4. So this graph will have 16 vertices. What's the valency? This vertex will have 3 neighbors on the row, 3 neighbors on the column, 6. Any 2 adjacent vertices like this and this, they will have 2 common neighbors here, and they cannot have any common neighbors here, so there will be 2. And any 2 non-adjacent will have 2. So for this graph, if you do the distance diagram, you have a 1, you have a 6, and you know what you're going to have here because it's going to be 9, because there are 16 vertices in total. And then 1 forward is 6, 1 back is 1. Inside this 6, you see what this 6 is this triangle and this triangle. So it will be 2 regular. And so it tells you what you're going to have forward. Because it's 6 regular, 1, 2, this has to be 3. 6 times 3, 18. 9 times 2, 18. And here, 4. Okay. So for this graph, this is this lattice graph or Hamming graph. There is a graph with the same parameters. I can, look it up and give me a description in the afternoon. You can get 2 donuts extra. If you find out, this is called the Shikande graph. So Shikande graph, there will be a graph that is not, so it has the same parameters, 16, 6, 2, 2, but is not this one. How can it be? Well, look it up. So Shikande, this is the smallest example where you have 2 graphs, 2 strongly regular graphs with the same parameters, but non-isomorphic. The graphs will be non-isomorphic. So look up Shikande graph, okay? Okay. Let me do a few more pictures and then we'll be done. Okay. Have you seen this graph? This way. Yeah, it's a platonic something. What is it called?
Icosahedron.
Icosahedron. Very good. This is icosahedron. Again, the picture is 1,000 words. Can you say from the picture if it's distance regular? You could try to use that picture, but I did so I can draw it from one vertex. So you can pick a vertex. It should be here. It should be here. It should be here. What's from the picture? What's the valency? What does the valency look like? I might have messed it up a little bit. Yeah. Let me. Oh, sorry. Something like this. Okay, something like this. I think this works, but look up isohedron. I have it nicer here. So this is a 5 regular graph. Now, if you pick a vertex, each neighborhood is a cycle C5. Okay, and then the second neighborhood is also going to be like this, and you have something on the other end, and you have something like a cycle C5 in between the parts, and you have something here. So for the icosahedron, it's a distance regular graph. You have this diagram: 5, 1. Here, this is 5. Inside here you have a 2, and this is 5, this is a 1, and then you have a 2 and a 2 and a 2 and a 1 and a 5. So that's that one. And then one more. Which one is this? If it's the icosahedron we did, is the other one. The dodecahedron. So here, what do you have? You will have the distance picture is a bit more. I tried to do it in latex sticks, but it's probably, well, I won't do it. I'll just give you the distance, the diagram. You will have 1, 3. Maybe. Then you will have 6. Then you will have 6. And then you will have 3. And you will have 1. And okay. Figure out the numbers for them. Okay, so let me tell you one more thing. Okay, so there are many examples, but we're not going to draw this all the time. Now, so what happens from this distance partition? It's equitable for every vertex with the same quotient matrix. The quotient matrix will be something that is going to be d plus 1 by d plus 1. And it will be a 3-diagonal matrix. You will have entries on the diagonal, just non-zero entries. Well, yeah, the non-zero entries can be on the diagonal, above the diagonal, or below the diagonal. So here you will have 0k 0 0 0, and then you will have c1 a1 b1, and then it kind of goes like this: c2 a2 b2, and it goes down like this. The last row will be cd ad. Okay, so this is kind of, and zeros and zeros. Now, this matrix is a d plus 1 by d plus 1. By the stuff we did with equitable partition, any eigenvalue from here will be an eigenvalue of the big graph. And we did this for Peterson graph. We did this argument. Now, what happens in more general terms for all distance regular graph, number one, this matrix B has d distinct, d plus 1 distinct real eigenvalues. So for Peterson graph, diameter is 2, the matrix was 3 by 3. For any strongly regular graph, this matrix will be 3 by 3, and you will have 3 distinct eigenvalues. One eigenvalue you will always know easily, because the row sums, these graphs are regular, the row sums will always be k, so the largest eigenvalue will always be k, and it's usually denoted by theta 0, and then you will have theta 1 all the way to theta d. Now, the fact that they're real, you can do the same argument that we did for in the quotient matrices for equitable partitions, that the matrix may not be symmetric, but will always be similar to a symmetric matrix, so therefore has real eigenvalues, okay? Now, what will happen is that to the adjacency matrix of gamma, the distinct eigenvalues of A will be these eigenvalues. So the distinct eigenvalues of A will be these ones. So from this quotient matrix, you can get the whole spectrum of your graph. Okay, of course, you wonder about multiplicities. You can also find the multiplicities there is a formula for that. But from this, for the Peterson graph, you look at the 3 by 3 matrix, everything in there will give you any distance regular graph, you'll have this partition, and it will give you these things. So there's more research here, so I have some notes. I thought I'd tell you a little bit about this. Maybe, I don't know, we may do a little bit in the afternoon about it, just because, this topic may seem a little bit intimidating at first with these B0, C0s, and so on. So I thought I'll mention something before lunch, so that maybe we can I might tell you a little bit more about it in the afternoon. So I think I'll stop here and we can continue something for the last session in the afternoon. Okay? Thank you.